Anonymous functions have been a feature of programming languages since Lisp in 1958. In several programming languages, they are introduced using the keyword lambda and are often referred to as lambda or lambda abstraction or lambda expression. In Java, these are known as lambda expressions and are Java's first step into functional programming. Let's now try to understand the need for them. So here I have an interface fly behavior which has method fly, and I have test class myTest in which I have declared a variable flyway whose assignment is an anonymous class implementing fly behavior. I have another static method whose implementation is that of low flying behavior, which is similar to what is present in the anonymous class. Everything looks okay so far. Let's look at this anonymous class once again. It has the implementation of an interface that contains only one method. For such simple classes, the syntax of this anonymous class adds a lot of noise and makes it less readable. But then since Java 8, there are easy ways to express single method interfaces in a compact and readable manner. And this can be achieved with the help of lambda expressions. Let's have a look at it. Now, as you can see here, we have been able to convert these 6 lines of code into 3 lines of code with the removal of implicit syntax from the anonymous class. And you can see here how lambda expression has helped us address the bulkiness of this anonymous inner class. But then, in certain cases, lambda expressions might merely act as a pass-through mechanism, such as by calling another existing method or constructor. For example, here we could have simply called the static method flyLow rather than writing system out statement here. In such cases, we can simplify lambda expressions even more using method references. So as you can see here, it is as simple as myTest flyLow. So method references are compact, easy to read lambda expressions for methods that already have a name, in this case flyLow. Now this means that every method reference will have an equivalent lambda expression to it, but vice versa is not true. We will talk more about method references in more detail in another video. Put it another way, think of lambda expressions as anonymous methods without a name. So this was method fly from the interface implementation, but it has got no name. And think of method references as easy to read lambda expressions for methods with a name. So this is my test's flyLow method. Let's now talk more formally about what kind of interfaces can be replaced by the lambda expression. Let's have a look at the interface fly behavior from our previous slide. What's so special about this interface? Well, this special type of interface that provides target type for lambda expressions is known as functional interface. And what makes this interface a functional interface? Well, it has exactly one abstract method, fly in our case, but there are more rules to it. Default methods don't count, which means you can have as many of them as much as you want. Similarly, static methods don't count, and you can have as many of them as much as you want to. And the last one, which is any public method of Java object doesn't count. This is because any implementation of the interface will have an implementation from object class or elsewhere. And to add to our convenience, Java also provides an annotation functional interface which helps us abide by these rules all along. With these in mind, let's dive into a quick demo to understand functional interface. Okay, so let's make this interface a functional interface and see how does the annotation functional interface helps us abide by these rules. So let me annotate this interface as functional interface. And from this point on, it's the duty of the compiler to throw an error if there is a violation. To demonstrate this, let me break rule number 1, which says it has exactly one abstract method. And you can see that the compiler is throwing error. That is because it has more than one abstract method now. So let me get rid of this now, and everything is okay again. Rule number 2, default methods don't count. So let me create a couple of default methods now. Now you can see that I had created a couple of default methods and it is okay as per the definition. And a similar idea holds true for static methods as well. And it is okay too as per the definition. The final rule says that any public method of Java object doesn't count. This is because any implementation of the interface will have an implementation from object class or elsewhere. So let me write a method from object class and everything is fine. Now if you are looking to create your own functional interface, I would suggest you look upon the ones provided by Java. You might have already seen Runnable since version 1 and Comparator since version 5. And there are many of these in different packages until Java 7. But since Java 8, with the introduction of Lambda expressions, a host of functional interfaces have been created and are put inside the package java.util.function, categorized as predicates, suppliers, consumers, and functions. I will talk more about these in a separate video. Let's now look at the Lambda expression syntax in more detail. So here I have an interface is greater which takes two numbers as input and outputs a boolean result. Now if we were to implement this interface, it might look like this. With this in mind, let's look at the syntax of the Lambda expression. It consists of three parts: argument or input list, arrow token, and the body. The argument list is int x and int y from the interface. Next is the arrow token, which is always a constant. And finally, the body, which is exact copy paste from our concrete implementation. Let's now look at how would the Lambda expression look like. And here it is. The argument list followed by arrow token followed by body in curly braces. And you might have noted already that the Lambda expression doesn't have a method name is greater anymore. Now that you understand the basic components of Lambda expression, let's understand the different syntactic flavors of argument list and body. So here let's just forget about the body and focus only on the left hand side of the Lambda expression, which is argument or input list. Now consider this as signature of an abstract method of functional interface. I had omitted other details of interface such as its name. Now since this method has no arguments to process, argument list can simply be a pair of round brackets. Next we see that the method takes an argument of type integer. We can simply put that between the round brackets. And just to avoid confusion, we can also rename the variable here. We can even simplify this further by getting rid of the type, which can be inferred by JRE. And above all, there is no need for the brackets too, and it can be as simple as x followed by arrow token followed by the body. These all are the different versions of a single argument. Let's now move on to cases with more than one argument. As we can see that this method takes two arguments of type integer and string. So we can simply put both of them between the round brackets. And just like our previous case, GRE can infer the type of these arguments and you can get rid of types in the argument list. And on similar lines, methods with 3, 4 or more arguments can be dealt with exactly in the way we have treated the method with 2 arguments. Let's now understand different ways to write the body part. So here I have a method that takes an integer input but returns nothing. So you can write the body of lambda between the curly braces exactly in a manner you would have written a method body. Next up, the same method signature, but this time it has just a single statement in the implementation. All same as the previous example. But then there is an easy way to write implementations with a single statement. and that you can get rid of the curly braces and everything is there in just a single line. Next, we have a method that takes an integer input and returns another integer. Similar to our previous styles, we write everything in curly braces and write the return statement. This next example is same as the previous one except that it has just a single statement in the implementation, no problem whatsoever. But again, there is an easy way to write implementations for the single statement where you can get rid of the curly braces and the return keyword, and everything is there in just a single line. With these in mind, let's quickly dive into a demo to understand Lambda expression syntax. Let's look at the functional interface first. Here I have an interface onClick listener with one abstract method onClick. I have created another class view which has a member variable onClick listener. This can be set using this method. Further, when someone clicks on this view, it internally invokes onClick listener's onClick method. Also, I have my test class here. It invokes these three methods. Number one, instantiate views. This initializes all my views in this class. Next is setup click listeners, which should set up click listeners on those views. We would implement this method shortly. And the last one is perform clicks, which performs clicks on all the views of this class. Let's now implement the method setup click listeners. So here we would set up click listener on submit and refresh button one by one. Let's write code for those. Let's run this code and you can see the print statements here. Now let's replace the implementation of Lambda expression in another method. First, the argument list. Let's simply copy paste it from onClick's argument list, which is simply a pair of empty round brackets. Then the arrow token, and let's copy the body from onClick's implementation. Let's do a similar exercise for refresh button. Let's rerun the code and you can see the print statements here. Now, since the implementation body of the Lambda expression contains just a single statement, we can further get rid of curly braces too. Let's run the code once again and see the output. And it's the same. You can even pass local variables from the method and instance or static variables from the class in the Lambda expression. So let me create some variables here. And on similar lines, let me create an instance variable of parent view name which we would use in the Lambda expression. Let's run the code once again and the output is just fine. Now, another thing to note about Lambda expression is that you can declare them as variable and even pass them around just like any other variable, which means they can serve as functionalities or data being passed around. So let's create variables for these Lambda expression. So what I have done here is passed on the Lambda expression functionality as argument or code as data through these variables. Let's run the code once again. And the output is as per the expectation. And while we think of variables, we can even return them as method output. So since we are using single print statements here, let me create a utility function in view class which returns a utility on click listener. So let me copy from here. Let's assign it to one of our variables here. Let's rerun this code one final time and see the output. And here are our print statements. Now that we have seen some variations to no argument method of our functional interface, let's see different variations to single argument method. For that, let's introduce another argument animate in the method click, which we would propagate all along through view to our test class and interface. But with this, our existing lambda expressions have started to throw compile errors. Let's fix them by introducing the argument animate. Let's run this code and see the output. And here we have the output with the variable animation. Next, let's get rid of type argument list, which is boolean type here, as it can be inferred by GRE. Let's rerun the code and see the output. And it's the same. And finally, let's simplify it even further and get rid of the round brackets too. Let's run this for the final time and see the output. And it just works fine. Let's now see the different syntaxes to write more than one argument lambda expression. So let's add the hit coordinates x and y to our click method here and fix the code in perform clicks method and correct the signature in interface 2. Let's also return a boolean value to tell if the click was a success or failure. Let's fix the interface method as well. Let's put some dummy values here. Now since the click method returns true or false, let's add a variable boolean which tells us if it was a success or failure and print those statements. Okay, now let's fix our lambda expressions by introducing the variables x and y. And let me put a dummy condition here where I'm saying that if x is greater than y, return true, otherwise false. Similarly, let's fix the arguments here as well. And let's return true here always. Okay, now our setup is ready. Let's run our code. And as you can see here, we pass the animation as true and false here, and the output is true and false here. Similarly, it was a success here as we are returning true always, and failure based on the condition of x and y here. Okay, now let's get rid of types in the argument list as they can be inferred by GRE. Let's run the code another time, and the output is exactly same. So let's do a quick recap to what we had learned so far. We first looked at how can we reduce the syntactic burden of single method anonymous class using lambda expression and method reference. Next, we looked more formally to what makes an interface a functional interface and looked at a demo for the same. And finally, we learned how to write lambda expressions with different syntactic flavors of argument list and body. With all this foundation set, I will talk more about method references and Java's inbuilt functional interfaces in another set of videos. Thank you.